Today we're going to present our senior design project, which will be about designing and implementing of a novel real-time wearable system for early detection of diabetic foot ulcer. I want to introduce myself. My name is Abdulrahman Ansari and my colleagues Ghazi Abu Samah and Sakim Mahmoud. I want to thank our supervisors, Dr. Muhammad Choudhury and Professor Farid, and also I want to thank our examiners. According to these statistics that has been done by Atlas in 2019, they mentioned that 1 out of 11 adults they are having diabetes, and 15.6% people in Qatar they are suffering from diabetes. 60 million people globally with diabetic foot ulcers. 2% of the people they get DFU annually, and 1% get mutated. More than 10% diabetic patients in Qatar they are having diabetic foot ulcer. Diabetic foot ulcer mainly caused by two things: diabetic neuropathy, which can cause or damage the nerve, and diabetic eczema, which is the vertical damage. Our project mainly will concentrate more on the nerve damage. The diabetic foot ulcer affects three things: vertical ground action force and guide cycle and the foot temperature. The guide cycle can be measured by two things: vertical ground action force reading and the IMU. The guide cycle, the vertical ground action force and the foot temperature will be analyzed to forecast the diabetic foot ulcer. There are four common types for detection techniques to detect the diabetic foot ulcer. Type 1 was for the clinical advice, and type 2 for the imaging techniques, and type 3 clinical non-advice techniques, and type 4 of the smart techniques. Mainly the type 4 is our project will try to meet, because they are concentrate more on the VGR and foot temperature. As for type 3, it is clinical but not advice, that they are using some break sensory threshold or vibration protection threshold testing. And also type 2 is the imaging techniques. They're using some radiographs or magnetic resonance imaging. And this table shows the performance between the type 4 types. As you can see, the type 4 is mainly better than the previous three. As you can see, that this can be real time, and this accuracy, and it's reliable, and also it can be portability, and also it can be monitoring from home. It doesn't cost too much, and also the patient can afford it. Unlike the type 1, it cannot be monitored from home, it's not portable, cannot monitor from home, also cost too much, and the patient cannot handle it or afford it. There are two install available in the market, but the problem with them, they are cost too much. Like for the F-scan, they around cost for wireless F-scan is like cost $20,000 US. So Multicon for analyzing guide cycle would cost around 7,000 Qatari. After checking many research and communication production, it was found that previous work did by the research, some analyzed guide cycle by the GRF or the MU, others analyzed the tomography or the foot temperature. A few researchers work on the machine learning, statistical analysis, or even affect the data gathering. But combining the machine learning to classify the data collected by the constant smart install and data logger is completely new novel. Our main objective of the project is to design a smart install for vertical ground action force, also to check the guide cycle and for temperature monitoring, and make it wireless transmission of the sensor to the central device for peripheral using low consumption protocol. And we require large data sample to apply machine learning to classify the subjects based on the DFU sensitivity class in real time. And this is the project constraint. As you can see, it will be wireless data to avoid any robustness, and you will use force and temperature sensor because they are flexible, and you use rechargeable battery to minimize the maintenance costs, and the input voltage between 3.3 to 5 volts, because this is what the sensor can handle. The PCB size will be 5 by 5, and the weight will be less than 200 grams, because we want to avoid any effect for the guide cycle. And the volume costs, so the DB budget 10,000 Qatari, but the production cost will be around 150 to 200 US dollars. As for the safety, you will try to protect the battery from any overheat or any leakage, and you will try to make the circuits inside the box and the install more smoother, and it should be finished within 8 months. As for the design procedure, it will be four main things. We have data acquisition system, data logger, and machine learning, and the classification of the subject. And now my friend Qazi will continue from here. Thank you.
This is our final data acquisition block diagram So what is happening there is that when the 16 pressure sensors and temperature sensors obtain the patient's measurement, the data will go into a buffer, then being multiplexed in order for the microcontroller unit to transfer it to the central device using BLE. Here we can see a real picture for both sides of the final install, top and bottom, after rearranging them to make it in a better appearance. This is the top view, and this is the bottom view with the ribbon cable. For the temperature sensor calibration, this is the calibration curve of the resistance versus temperature given by the manufacturing company of the sensors. So from this plot, we are able to get the Y equation and use it to convert the analog values we obtain from the temperature sensors into temperature values. For the wireless communication protocol, we have used Bluetooth low energy BLE, which served us perfectly. As it meets many of our constraints, it has a very low latency, as in band 2.4 gigahertz, can have a transmission data rate of 1 megabits per second, a good range from 10 to 40 meters. It consumes very low power and also robust. In addition, ESP32 was selected as it's very efficient for our purpose and has many great features, like it comes in small packages. It has an active online community. It supports Bluetooth 4.2, and most importantly, it's low in cost. In the previous SDP, the data was used to go from the peripheral B to peripheral A and then to the client. So if peripheral A is not working for some reason, then the whole system is down. But for our case, we have made each peripheral to transfer the data independently to the central device, client A and B, to have a robust transmission while transmitting a large packet size. The code was firstly done in Arduino IDE, then we switched to platform IO IDE because of its better debugging capacity, better terminals, better visuals, and most importantly, to manage the codes as a project. Now we have all libraries in that project, which we modified. If we want to share the code to someone, maybe a hospital, we can just send everything in a single folder. The microcontroller called TinyPico ESP32 module, which satisfies our selection criteria. First, it has very small size, as you can see. It's barely bigger than a coin. It has enough general input-output pins. It consumes low power and has a cheap cost. It can be coded easily. It's breadboard friendly, which is very important for our case, as it can be connected easily to the breadboard to be tested before it's fixed on the printed circuit board. It has constant voltage output using embedded LDO, and finally, it can charge a battery if needed, which is great as well. Selecting the correct battery that meets the constraints of the project is an important step. So this was our selection criteria for the battery. Having a certain voltage output of 3.7 volts that works well with the PCB components. Being able to recharge it in order to minimize maintenance cost. Having more charge cycles for a longer lifetime of the battery. Being able to handle peak current, and having a protection circuit in order to have protection against leakage of and as we can notice, the new PCB has improved significantly by using SMD components, which are very small, and the proper use of top and bottom layers. As a result, the area has decreased 48% compared to the older one. Height and weight have decreased as well. Eventually, smaller PCB with a smaller height and weight will afford more comfort to the patient as it's mounted on the leg. Now, moreover, the new PCB doesn't have only a smaller area, but more options, which is a good accomplishment, I believe. So there are 4 more features new in this model. In addition to the BLE wireless communication protocol and acquiring 16 points of the GRF, we can now acquire temperature of 8 different points on the foot. There are no buffers. There are buffers to remove loading effect. Power is managed better, and we can charge our battery. And an inertial measurement unit is used as well. In this picture, we can see the new PCB model with all components soldered on it, and the different views from top view, side view, and how the ribbon cable fits perfectly on the PCB. So a software called Fusion 360 was used to design a box that's going to contain the PCB. As you can see in the picture here, all the features of the box are compactness and the smooth looking. PCB can be fixed tightly inside. Edges are not sharp. There is a hole for the ribbon cable and another hole for the micro USB cable connecting the PCB for code uploading or charging. And it was tested thoroughly for debugging 3D printing related issues. You can see here how the box is going to be mounted on patient's leg and how it looks from the inside. After going through the data acquisition process and transmitting the data to the central device, we reach the data logging stage, and I will leave the floor now for Sakib to continue. Thank you.
Yes. So as my friend Ghazi was explaining the data acquisition subsystem, it was sending the data to a central device, and this data needs to be saved somewhere so that we can use in the future for machine learning. So that's why we have devised a data logging system. So data logging system, it takes the data from the data acquisition system and saves it to the computer. So the data is coming to the computer through the COM port from the central ESP32, and we have the coded for a Python script which can save the data to Excel or text file, and then this data, as I said, can be used for machine learning afterwards. I have created a short demo for you to see. This is the peripheral code here. As you can see, it has like three codes. They are related to each other. The header code where I am bringing the libraries and also some classes and some parameters we need to set. This is the platform IO IDE, not the Arduino, but it's like much better for debugging and also to share the code in a good way, like in a project. This is the client side code. So here the ESP32 is receiving the data. So the data stream, you can see data stream is coming from both temperature and pressure. First 16 columns of temperature, then 8 columns at temperature, pressure and temperature. Then these are all the libraries we're using. Also same thing we're doing here for the client code. In this setup, I am just sending data from one FSR which is connected to the third pin of the multiplexer. So all the list of libraries, like it's also included in the project. When I press the FSR, you can see the values are changing. It should go maximum to 4095, which is 12-bit ADC from ESP32. Now before I go to the Python script, I need to turn off or kill this terminal here because it's communicating to the COM port. So because now this Python script will communicate to the COM port, otherwise they will conflict. I delete some of the text files I've gained from the first run of the codes, so to show that when I run this code, these files appear. So when you run this code, as you can see in the terminal, all the values are coming, and I'm pressing the sensor, and data is coming actually wirelessly, like just like our uh, data acquisition system. And in the text file, this data is already been saved. You can save it in anywhere in the computer, in location, depending on the location you put here. All the data and other text file are like null values because I'm not sending anything there. So dividing data into force and temperature for two legs. This is the code for the Excel file. Now it should save the data in the Excel file. So similar thing happen. I'll press the FSR and the values will come, and it will run the code until unless the 500 rows in the Excel file is fulfilled. So you can change this value to make the code run longer. So the code here in this case turns off automatically. Now see the first row is the level row. It's showing all the FSRs, 16 FSRs, and there are some is the same because all the other values are 0. So that's it for the data logger. Now let's move into the next section. After the data is being saved in local database, we can use that data for machine learning. The machine learning is was done in 5 steps mainly: data pre-processing, feature extraction, data partitioning, training, and testing. We could not collect data for the blockage, so we just use data from a past research. And in their research, they have saved data in a text file. They have like VGRF, EMG, and some other data. Only this full data for us was the data in the third column. As you can see, they had 76 patients, on 20 on control, 20 on diabetic, and 34 ulcer. Now we cannot use the raw data from the text file directly. We need to create a metal data set at first. So it's the data set of the containing the raw data actually, but it can be used for feature extraction directly because of this plot. As you can see, the data, as you can see, like for three classes, they are not on the same part of the axis, and there are null values here, and they have different durations, and they have different magnitudes, so their features are not comparable. So we have to make something, do something so that their features you can compare. Then you can only extract their features and do the machine learning. So what you do is we segment the data, normalized it. um, then what happen if you plot the same data? See, the now the data is within the same location of the time axis, like same starting ending point 0 to 1024, and they are normalized between 0 to 1. Now their features are comparable. So here we have attempted to plot in their data separately, like control, diabetic, and ulcer, and also we plotted their mean and standard deviation plots. And this is the VGRF matrix 1024 times 76. 76 means the patient, 76 subjects. We also plotted their PSD plots, power spectral density. It determines at which frequency their most power is there, like their working frequency actually. So also we have plotted a similar thing here. This PSD array 76 times 1 array and the VGRF matrix, we need both of them to produce the feature matrix here. As you can see, the code is snippet. This function takes in the input from all VGRF and FSN matrices. It produces a new matrix, feature matrix of 76 times 33. 76 is the number of subjects and 33 is the number of features we're using here. Like there are 33 features, statistical feature, mean, median, and other features. So you can check you can take you can even more features or less features, but like more features are normally good for machine learning. Now we have to add another column, which is the label column, which shows the true class of the particular subject, so that we can find the test accuracy afterwards. So after that, we divide the data into train and test fold. We do it randomly, like we take 80% of data for training and 20% data for testing. We created 5 folds, you can create more, but yeah. So for test fold 1, we have to test it in terms of 10 fold 1 for whatever algorithm is it. We cannot test for other thing because it's randomly produced, and if we check for other folds, some part of the test fold will be there in the 10 fold also, so it will give you a high accuracy but high performance, but it's like faulty. So here is screenshot from the MATLAB classification learner. You can see this is like we have trained data for many algorithms, and their relative performances, as you can see. And fknn is like giving the best performance. In this case, 88.5% is the training accuracy. So after training, we need to test. So after testing, we got this output in the MATLAB. So these are no labels, these are predicted labels from the machine learning. So as you can see, if you compare, these give the correct prediction, this is wrong, then again correct, this again wrong. So based on this one, we found the confusion matrix. And also these 4 parameters: accuracy, precision, recall, and F1 score. As you can see, control performance is better, and it will be better for in our case for almost all cases. But diabetics performance is like low for recall and F1 score. So if we look at the performance for all the cases, you can see for control the performance is not bad. FKN is always winning here, but the support vector machine is also doing good. For diabetic, as you can see, the accuracy and precision are good, but like recall and F1 score was low. And then for ulcer, it was more or less good for all the sectors, but like not excellent performance, but it's good, acceptable. So if we summarize the performance for all the algorithms, as you can see that in the for the control class, the performance, highest performance was no, average performance was like more than 90%, and best performance was FKN all the time. For diabetics, there are some for recall F1 score the performance was bad, but accuracy gave like a medium performance. And for ulcer, overall the performance was medium, but FKN, the find K nearest neighbor, was the winner or the second place all the time. Like it's like a suitable algorithm for our case, seems like it. Now why diabetic is giving lower performance, we'll explain it later in the conclusion section. So after machine learning, we did the cost analysis. So our device is costing in total 1600 QAR. As you can see, the lion's share of this cost is covered by the FSR 960, so it's like around 65%. So if we could get rid of the FSR in our insole, then and we get the pressure rating by some other means, then it would decrease the cost by a great amount, like if the cost of the new material is less. So the alternatives are what? So let's look for it in the conclusion sections. So as conclusion, we're going to say that the hardware section needs to be finished because it's not 100% finished, because the queue closed before we do it. and more subject data should be collected for better training and testing of the machine learning. As we have seen that the diabetic patients one are giving us good result because there's an ambiguity, like it has some traits of the common people and also some traits of the other people, so the algorithm be confusing it between either ulcer or the control. So if we have more data, like more than 500 data, we had like only 76 patients here, then it will give a better performance. Also we could test that if we had in our hardware, as you were saying, we have option for IMU. We have seen that if we done same thing for IMU, then if it increases the accuracy and precision or not. Also we have to incorporate temperature data in our final results to give us a better outcome, like more certain outcome. And we can design a GUI app so that it creates an easy user interface. And also for about swapping the FSR, we could explore the graphene and optical based install options, so that can make an even lower cost install. So that's it for our senior project presentation. Now, if you have any questions, we are here to answer.